Let me now give you some programming hints in terms of how to drive these motors. With the BLDC motors, you really need to make sure that the magnets are aligned to the pre-aligned to the coils to get the maximum torque at the startup. And you can do that by energizing two of the coils. So you energize, let's say, these two coils, and then you brake after, say, 100 millisecond or 50 millisecond. So you provide a short duration pulse on two of the phases and do a sudden brake after that. So when I say brake, it means you clamp all three of them to the low side of the network. So if you were controlling these three phases with this sort of H-bridge, three-phase bridge arrangement, you would say pulse these two first, and after a short period you would clamp these three the three phases down by turning these MOSFETs on, and that would essentially pre-align the motor. Now after you've done that, after you have pre-aligned the motor, you then want to ramp up in open loop. So let's go back here. So you have a startup alignment. Let's call it pre-alignment. Then you have a active brake. Then you have a ramp up scenario just to get the motor going. And this ramp up is usually done open loop. So you know, depending on the size of the motor, you would know there would be a chosen duty cycle that you would choose. Let's call it 5%. So you choose a duty cycle of 5% and a frequency of, let's say, a ramp up frequency from 0. So what you want to do, let's say 1 revolution per minute, 1 RPM, down to up to 240 RPM. Now this can be a little bit confusing. I have read different texts out there, and people seem to have different understanding. There is the electrical RPM, and there's the mechanical RPM, and these two are different. Depending on your construction of the BLDC motor, for example, let's say I pick this one. This is the underside of the BLDC motor. You could have potentially 4 to 12 pole pair, and these are the actual permanent magnets, which is probably not so easy to see, but the permanent magnets mounted on the side of the wall. And they can the relationship between the electrical and the mechanical RPM is that your mechanical RPM, MRPM, is electrical RPM divided by the pole pairs, so P. So if you have if you want to drive a motor with a mechanical RPM of let's say 3000 RPM, mechanical RPM, then, and say you have a pole of 4, so you have 4 pair pole, your electrical RPM would essentially be 12,000. So that's RPM in minutes. Therefore your electrical RPS, which is rounds per second, would be this divided by 60, 200. So that's how many rounds per second. Now this of course means you have 6 different commutation states. You would have this times 6, in other words 1200 pulses or state changes. So let's go back to these ramping up in open loop. So you want to choose a 5% or so, or anywhere from about 2 to 5% just to get the motor running, duty cycle. And then you want to choose a frequency that you can start rotating the field in, and this frequency can be chosen, somewhere in that order, in this 200 RPS or less. So you would be increasing the RPS from the start, so from the stall position. Now the way to do that is to configure a timer to generate these pulses, or change these pulses across the 6 output pins of your microcontroller. You can basically configure a timer, and if you've seen the way the microcontroller timers are done, so the timer basically, it keeps ramping up, and what you want to do is at one instance you want to change the update the timer value here, so it resets itself and then goes on to the other one, and you want to update the timer again, so it changes its period, therefore that leads on to the other the next timing. So then you want to reduce its period again, and so on. So this will keep changing. The period for timer will keep changing, and by reducing the timer period, you're essentially changing the frequency. And if you set up a timer interrupt in your microcontroller, then and within the interrupt you could call the ramp up function, which basically goes from one combination of pin to the other combination of pin. We'll talk a little bit briefly about these combinations. So if you remember the famous commutation steps, 6 commutation steps, your phase A, phase B, and phase C. You have phase A, stage 1, high and high, then it goes through a zero crossing, comes back down, another zero crossing, so you have zero crossing here, and going up, zero crossing here again. You have phase B starting from the bottom, goes through a zero crossing, up, and another zero crossing, and then down. So these are the zero crossing areas. With C, it will start from there. Let's say start there and there. So that's just a common standard. That's just the famous trapezoidal shape that you've seen before. If you've done some studies on the net. So this is your 6 commutation stages. So you have 0, 1, 2, 3, 4, 5, and then rolls up from 0. So you're from here to there, this is your 1 electrical revolution. To achieve this sort of waveform coming out of your microcontroller, logic outputs, you need to make sure you work out these, or you translate these waveforms across the pins. So to do that, you have to create a drive pattern. So for example, if you consider this to be your the first state or zeroth stage, then your drive pattern for pin A, so you would have multiple pins. Let's say you have A low, A high, B low, B high, C low, and C high. So you need to create a drive pattern which has at zeroth stage, let's say your zeroth stage will have A high would be on, and your B low would be on. That's your zeroth stage. Then your first stage would be your A high still high, and your C low being on. Now these of course correspond to the original MOSFETs we had, so you would have A high, A low, B high, B low, C high, C low. So they're the ones you're essentially trying to turn on or off. So then you would have the second stage, you would have the B high and C low, and third stage your B high and A low. Fourth stage is your C high, A low. Fifth stage is your, well, this is really the sixth stage. You will have C high, B low. Okay, so these are your 6 different stages, so you need to make sure you fire the MOSFETs using these stages. Now of course if you can have counter clockwise rotation, or you can have clockwise rotation. If you do counterclock, you'll need to do some experiments with this, but basically with your counterclockwise you might be driving, let's say, from this end, or if you do clockwise, then you might be driving from that end. So this would be your zeroth state. What I've done in my program is I've got a state machine function, and basically with the state machine function I have a starting state 0 all the way to 1, 2, 3, 4 and 5. So at the end of each state machine I go to the next stage. Now within each stages of the state machine I basically do a drive pattern assignment, and I also set up my next ADC mux, because as you are updating the output to your pins, you want to make sure what happens in your next because as you're updating the output pin, so for example at the start of stage 0 you're updating your output pin here and output pin here. So at this instance your output pin A has gone up, B has gone low, but following that you want to make sure that you're monitoring for this back EMF on phase C. So in stage 0 you assign your next ADC multiplexer should be set to monitoring phase C. Okay, so when you move on to the state 1, then you go on to you're updating your pin here and there, but also you update the mux to B. So here, state 0, your mux would be set to C, monitoring phase C. At 1, your mux would be updated to monitoring B, and then ADC mux would be updating to A, and following that it would be back to C again, and then B again, and A again. So it's a rotating chain. And of course, if you're doing this counterclockwise, then you'd be going the other way around, so your states would be reversed. And within each state, don't forget that you have to update the drive pattern to move on to the next state. So, drive pattern. And so on. So what you want to do next is you want to have a closed loop scenario. So you finish the ramping up, and once you've gone to a stable rotation, you jump onto a closed loop control. And in this control, you basically leave your last duty cycle, in closed loop. You basically run on the last duty cycle, and you stopped updating the drive pattern, so you no longer update the drive patterns. You wait for a brief period of time, and during that wait you hope that your zero crossing would be found, and once you find the zero crossing, only then do you update the drive pattern. Otherwise you don't. In your open loop, you don't look for the zero crossing. You basically keep updating the drive patterns every nth millisecond, or however whatever frequency you chose earlier on. Let's say 200 rounds per second. So you would be updating it every well, your frequency of update would be 1.2 kilohertz. So in the closed loop, you would not be doing that. You will be holding your last duty cycle, and you would wait for the zero crossing. So what would happen is you would update the last one. There's your holding of last update, and you would then turn on your ADC monitoring after a delay. So you don't want to turn it on straight away, because there's going to be you're bound to have some sort of a noise. So you want to turn on ADC monitoring of the phase back EMF after a slight delay, and once you've done that, then from there on you keep monitoring, and once you get the back EMF showing a zero crossing, only then you double basically the timer value. So you've waited this long to, once you've found the back EMF, you then double that wait. So you waited, let's say 20 microsecond. You need to then reset the timer to wait another 20 microsecond, and then finally update the drive pattern. And once you've done that, you repeat the process. So you wait a little bit longer, a little bit for the noise to die down, then you activate the ADC again, and by that time you've gone to the next mux, and your next mux is saying that you should be looking at on B phase. Your ADC value is from B phase. You then wait and find your zero crossing. Once you find it, then you wait another same time, and therefore you go on to the next stage. So this is your closed loop. You're really no longer firing each of the pins based on your desired frequency, but you're really monitoring the zero crossing time, okay? And then depending on that zero crossing time, you're moving on to the next stage. Now this time would vary when you start varying the duty cycle. Why? Well, because if you start pushing the motor, if you go back to your bicycle pedal example, if you start pushing the motor phases stronger and stronger, by increasing the duty cycle, what would happen is that your zero crossings would start to happen earlier and earlier. So what you're doing is you're changing the interval. You're changing the interval between the states, and that has the effect of changing the motor speed or the frequency of the electrical RPM. And so this is how you control the motor in closed loop, by controlling the duty cycle. So when you're writing your code, you need at least 3 interrupts. You need the ADC conversion complete, then you need a timer, let's say timer 0 A interrupt. Then you also need a timer 0B interrupt. So what you would do is you would configure, you would set up your timer A interrupt at this instance. As you come off from ramping up to closed loop control, you need to configure your timers such that timer B gets activated after halfway of the previous zero crossing. So for example, if your zero crossing was, let's say last one was at 20 microsecond from the commutation start, then your timer B needs to come on somewhere around halfway of that mark. So after 10 microsecond of the commutation, you need to interrupt with timer B, and at this interrupt you then turn on your ADC monitoring for the phase. So you start monitoring for the ADC, and hopefully after another 10 microseconds you would get the zero crossing. And once you've determined the zero crossing, you then remember how long it took for you to come across a zero crossing from the start of the commutation. So your timer value then will tell you what the zero crossing period was. And once you determine that period, then you basically double that period. Well, you update the timer A back again, so that timer A comes back again after another 20 microsecond. And following that, you just repeat the process again. So at the next commutation, you reconfigure your timer B so that it comes on another halfway, and once it is on, then you turn on your ADC monitoring again, and ADC finds a zero crossing, which then turns on the timer A back again, but only after another wait. So if this was X, then it would wait another X and turn on the timer A. And this is how you would be stepping through from one stage to the other stage. But notice how every single stage here is dependent on the detection of the zero crossing. Just a few words with the ADC conversion. A few microcontrollers I've looked at. Originally I did my design with Xmega 168. Later on I designed it with Xmega 32AU. Now these tend to have multiplexed ADC conversion, so you will often have ADC, for example 2 would happen way after ADC 1 was converted, and ADC 1 conversion would have happened after ADC 0 was converted. So when you raise the ADC conversion complete interrupt, you can only, you may just raise the interrupt at the second conversion, not there or there and there, because what would happen is, because they're multiplexed sequentially, by the time the second ADC is converted, you're guaranteed that your 0th and the first conversion would have happened. There's no other way will it have come to the second conversion. So by raising the interrupt only at the ADC2 conversion, you're saving yourself a lot of processing. I think that's as much as I could tell you about BLDC motor control theories. If you have further questions, just ask me anything down the comments section. I think at this stage I'll just run you through what I've actually done with my controller. So here's a demonstration of the version 2 board that I have made. It's been designed with a daughter board and main MOSFET board, so when it comes to experimenting with different controllers, it's easy to unmount this and put another controller board and hook it up to the MOSFET board. So leaving from the daughter board, you have the main 6 logic outputs and 3 phase inputs for ADC, and then 2 other inputs. One's the current reading and then the constant voltage reference. Sorry, the motor voltage full scale reference. The actual constant voltage reference is built in to this board, which is over there. Then you have the MOSFET board. Ideally you would want to have SMD MOSFETs mounted these days. These MOSFETs aren't really good because you have to have long copper tracks to accommodate all 6 bridges, and that means you have a lot of noise if you have long copper tracks. With the SMDs you can compact the whole construction into, I would say, half the size of this board, and therefore you would have a lot less noise. The noise characteristics on this board is much better than the version 1 I've had, but it's still nowhere near as good as it should be. Anyway, so over here you can see the ACS 758, which is the Allegro Microsystems current sensor, and there's your 12 volt to 3.3 volt converter, which then supplies the microcontroller through this. You can also see the 3 high side low side drivers, and they are these are the voltage divider networks for the ADC inputs. Let's run this